Okay, in this video we're going to talk about Chapter 3, when lines meet and you have linear systems. So 3.1 talks about interpreting the intersection point of linear and nonlinear systems. So if you look at figure 3.1, that is a non-linear system because the lines here are not truly lines. So the functions are kind of ragged lines, but you can still notice that despite the ragged lines, you can clearly see they intersect at the point P. So what is going on there? So at that point, the two curves come together. So what are they? In 1981, which is what the year is when these two come together, we see that the Y value is 50. So what is this? So the title is Percent of All College Degrees Conferred on Females and Males Between 1971 and 2017. So at that point P, in the year 1981, there was an equal number of degrees conferred on females and males. Now look what happens after that year. There was a separation between females and females are projected to graduate at a higher rate than are males. So this is an interesting little tidbit, but it is a discussion point for nonlinear systems and finding the point at which they intersect. So prior to that intersection point, so prior to 1981, the females were graduating at a lower rate than males. So that is your takeaway on that problem. So here's a quick summary of what we've just determined. To summarize, the percent of females receiving college degrees has been steadily increasing, and in 1981 was roughly equal with the percent of males receiving degrees. By 2017, the percent of females is predicted to be about 62% versus 38% for males. Now, the key point is you're going to use a straight edge to find the x and y values at the point of intersection, and be careful about reading these off the x-axis. Make sure you know what your units are and what your increments are, and you can do this algebraically as well, but in this situation we only have a graph. We're going to rely upon our ruler to get us our values. So when we had the nonlinear system, we had to rely upon the graphs to determine the point of intersection. But when you have a linear system, you have some more options. So you can use both the graphs and equations. And equations can be manipulated so that we can, in some cases, find a more accurate solution than graphs allow. So in this next example, we are looking at an economic comparison of solar versus conventional heating systems. So basically it's solar versus gas versus electric. So here you have your table. So you can see that we are looking at installation costs and operating costs. So just look at this for a second, and you can see that the installation costs for a solar system greatly exceeds that of electric and gas. But the operating cost for a solar system is much less per year than either electric or gas. So you're going to have a situation where solar is clearly more expensive, but eventually with the operating cost per year, you're going to find that they're going to cross, and at some point down in the future, solar will be less to operate per year. So you have this little table, but you also can get this little graph, this little equation. So you have an equation for each of them. So the installation cost is a fixed cost. It's also our y variable. The slope is the operating cost. So that's the cost that you incur every year. You only incur the installation cost one time, so it's not a yearly event. So once, as years go on, what happens is the installation cost is a smaller percentage. So you're going to have break-even points. So let's look at this on the next page. Okay, so just in terms of definitional type matters, This is called a system of equations. Okay, so it's a system of equations. So as long as you have two equations, you can have a system. In this situation, we have three, and as it says in the writing, starting right here, together they form a system of linear equations, which is a set of two or more linear equations. And we're going to work with this some more. And once you have the algebraic equations, you certainly could graph it and look and see where they intersect. But we also have the option to work with it algebraically and get a more exact value. And that's what we're going to be doing. Okay, presenting our information in a table gives us some interesting insights. So you can see, as expected, in year 0, you're just paying your installation charges, and you can see that solar is quite expensive. But now let's jump ahead to year 40. So in year 40, electric is $49,000, gas is less at $40,000, and solar is even less at $36,000. So the question is, where do these three different costs, where do they cross? So down here, we've expressed the information as graphs. So you can see we have the first graph has cost in thousands and then years. And you can see that we are starting at year 0, okay, and moving on to year 40. So the table matches the graph. So what do I see? I see a year about, about 16 or 17 or so right here. What's happening is that gas and electric are crossing. So where electric was below, now electric is above and gas is less. And then as you go on into the future, you have a crossing here and a crossing here. So you can see that as you go on in time, solar is actually the least expensive. And that's because its slope is the least steep. So once you get beyond the very, very high installation costs, the per year costs are very low, and therefore eventually we find that that is the best, the most efficient, the most economic system to use. It does take a while to get to that point, however. The next table right here just only compares traditional heating systems, gas and electric. And you can see that if you were going to buy a new system, it would be cheaper initially to buy gas. But then as years go on, all else equal, once you get to year 17, the electric system is, let me reverse that. It's cheaper initially to buy electric, but beyond year 16, 17, then the electric is more expensive and the gas is less expensive. And this means, all else equal. If you have frequent electrical brownouts or blackouts, then the headache of missing electricity on a regular basis somehow will outweigh the cost of the gas. So there are other things to be considered, but if you only consider the cost of gas and electric, this is what we're seeing. Beyond year 17, electric is more costly than is gas. And in this little slide, I'm just going to point out that we're going to practice solving systems of equations, these would be linear equations, using algebra, using graphs, and then also using our graphing calculator. So that is what's coming. Okay, on this slide, I'm really going to focus on this solution. So a solution to a system of equations. So if they say solve the system of equations, what they're looking for is a pair of real numbers which solves both equations. So you have one pair that is a solution to each of the equations in the system. So basically that's where they intersect. That is the solution to the system of equations. Not every system has a solution, and we're going to talk about that in a few moments. Okay, in these little practice problems for each of the following graphs, it says estimate the coordinates of the point of intersection. So let's see what we're doing here. If this is y1 and this is y2, and I'm going to estimate the coordinates. It's right here. So let's see. I don't really know what the units are, but I can see that at 1, so this is 1 for my x, and this looks like 1 also for my y. So at 1 comma 1, y1 and y2 are equal. So that is the solution. That is where they intersect. They are both lines. Okay, here the next one you have an example of a line, which is y1, and a parabola, which is y2. So I see I have an intersection here and an intersection here. So in this situation, I have 2 points of intersection, so let's figure them out. The first time they intersect is at, let's see, 1, 2. So negative 2 comma 0 is the first point of intersection. And then I see that y2 is below y1. And then they intersect again. Let's see if we can count this. 1, 2, 3, and 1, 2. So at 3 comma 2, they intersect again. Okay, so in this little graph, we talk about that this is another opportunity to practice using interval notation. So you can denote where y2 is above y1, where y1 is above y2, and you can use interval notation to use all of that. So where they intersect, one is neither above the other. They're both equivalent. So therefore, if I were to say, for example, with graph B, I want to know how the two graphs, the y2 and the y1, are related. So I can say that, let's see, we can say that y2 is greater than y1. Now read your x's. From negative infinity up to, but not including negative 2. So I'm going to use that. Okay, so then, because I said it's greater than or equal to it. Then I want to say, okay, what happens next? So y1 is greater than y2. Where does that happen? From negative 2 up to 1, 2, 3, positive 3, not inclusive. So what happens after that point? So after that point, what I'm finding is that y2 is once again above y1, and that happens from 3 to infinity. So again, you can use your interval notation to describe what's happening in our practice problems. Okay, looking at the next one, we have two lines again. You have a point of intersection. You can use interval notation again to describe what's happening on either side of that point of intersection. And then you have two nonlinear functions that are intersecting right there. And once again, you may use interval notation to describe what's going on. Okay, this is a rather important slide because we talk about the number of solutions for a linear system with two equations. So you can have one solution. So that means you have an x. Whoops, let me just do this. You have an x and you have a y. That is one solution. You have no solutions if the lines are parallel and distinct. Okay, so that means you may end up trying to solve for x and you get 5 equals 7, for example. That makes no sense whatsoever. You have no solution. The lines are parallel, and parallel lines will never ever intersect, and therefore they do not have a common solution. They do not have a point where they each take on the same x and y value. So that's important to understand. You could have infinitely many solutions, and that's if the two lines are exactly the same. So you might get an answer like 5 equals 5. That is true, but it provides you no additional information. That is your tip-off that your lines are the exact same line. They intersect at an infinite number of points because they are lying right on top of each other. Okay, so here you have the one solution, two lines intersecting at this one point. no solution, they're parallel lines, the slope is the same, so I'll say slope 1 equals slope 2. And then infinitely many solutions, which was our last scenario, and that happens when you have one line lying on top of another line. You have an infinite number of solutions, they are constantly equal, every x, y combination is exactly the same, and you can see that if you just look at the points along the line. You're going to have the same x and y for both lines because they are indistinguishable. So in that situation, you would have infinitely many solutions. Okay, there's another way to term that, and it's called inconsistent and consistent, and we'll talk about that on the next slide. Okay, so the way I have this slide set up, you can see that you have one solution. One solution is also called independent. No solution with parallel lines is called inconsistent. And infinite number of solutions, because you have the exact same sign, that's consistent but dependent. So consistent but independent is where you have one solution and the two lines thereby intersect at one point. That's consistent and independent. Inconsistent is the parallel lines, and consistent but dependent is the one line on top of the other. So in the first case, the inconsistent case, you have no solution because the lines are parallel, they never intersect. Like train tracks, go on forever and ever, never cross. The next you have consistent and independent. That's one solution. So you may have an x and one y, and that's one point of intersection. And the last is if you have infinite number of solutions. And that situation is where you have one line on top of another. Okay, so just to recap, what could happen algebraically if you have parallel lines? So you can end up with an equation that when you try to solve for x, you get 8 equals to 5, and that definitely is inconsistent with reality, and you have parallel lines. Consistent and independent, you will get x equal to some number. You'll plug that number in the original equation, and you'll get your y, and you have one point of intersection. Dependent situation, you might get an answer when trying to solve for x of 8 equals 8. That is completely true, but it gives us no additional information other than the fact that we have two equations lying on top of each other, and they intersect at every single point. Okay, those are very important factors. This is one way to think about it up top. This is a second way to think about it down below. You want to be available. You want to be able to discuss it from both vantage points. So given a linear system of equations, you have two ways that you are able to solve for it. And I use the word solve kind of loosely. You may not get a solution. Depends on what how the two lines relate to each other. So the first method we're going to talk about is the substitution method. So the example for that is right here. If you have two lines and one of them is in the y equals format, by substitution you can take your y and you can plug it in the first equation. That's going to have your first equation be written all in terms of x's. If you have one variable, you can solve for that variable. You will then get an x equals answer, and then once you have an x value, you can plug it in either equation, and really you should plug it in both just to make sure that you are getting the exact same answer. Okay, so this is solving by substitution. So just to recap, when you have a situation like the one I've circled in red, where one of your equations is a y equals, use that y equals to replace the y value in the first equation with the 15 plus 2x that equaled the second equation, and then that's going to make your first equation written in terms of only x's. If it's only written in terms of x's, you can easily solve just through your algebra for the x. Once you have the x, take the x, plug it back into either or both equations, and you should get the exact same answer. That is the substitution method. Okay, on this page from the textbook, we can see that they're setting us up to practice the substitution method. So they're going to have us rewrite each of these A, B, and C's in terms of y for the first two and in terms of x for the last. You're just really manipulating your algebra. Question 2 says determine the number of solutions without solving the system and justify your answer. Very interesting. So what kinds of things could you look for? Okay, if the slope is exactly the same as it is in A, what does that tell you? Slope is the same, parallel lines. You're not going to have a solution because they never intersect. So what else do I know? So I'm going to have no solutions to A, and it looks like since they're not parallel lines, although they have the same y-intercept, they're going to intersect at that y-intercept, and you will have one answer. All right, so you should be able to use the terminology we used on the previous page in terms of consistent and inconsistent and the number of solutions that we get. Okay, question 3 says solve the following system of equations using the substitution method. Okay, so let's just talk this through. What if I take the 3a, and wherever I have a y, I plug in x plus 4. So that's going to eliminate this y. It's going to give me x's on both sides of an equation. I can just do my 1 and 2 step problem solution methods and be able to get a value for x and then use that value for x in either of these two equations and get my value for y. Okay, so that's in essence what they're doing. So you can use either equation to substitute. Okay, in question 4, notice how they have one of the equations as a y equals or an x equals. So in A, you would use the y equals right here, and you would replace your 5y with 5 times paren x plus 3 for your second equation. Look at B. I see I have a z equals something. I would use that 3w plus 1 and replace the z in the second equation and go ahead and solve for w and then insert that w value into either of the equations to solve for z. Look at C. You have x isolated right here. Whoops, excuse me. Let me go back. Let's see what happened to that graph. Okay, so we're going to figure this out in just a second. Okay, we're back in business. So in C, I'm going to take my x and say I'm going to replace my x in my second equation with the expression 2y minus 5, solve for y, and then plug in to get the x value. In the last one, I would have to, if I wanted to solve for r, I would take the first equation right here and make that r equals 5 minus 2s, and I would substitute in for r in the second equation. Okay, so I've given you some ideas of how to do this. Go ahead and practice what you need to practice to make sure that you own the method called the substitution method to solve for r variables. Okay, here's a second method that's frequently used, and it's called the elimination method. When you use the elimination method, you either add or subtract your two equations. You might have to use a multiplier in order to make it so that when you add or subtract them, one of the two terms will cancel. So they have an example here, but we're going to look at other examples going forward. So let's go to the next page. Before I move on, I wanted to focus on these two equations. And I want to say that if I want to use the elimination method, what I would do is I could multiply the first equation, so equation 1, by a negative 0.07. So if you multiply every term by a negative 0.07, what's going to happen is when you add them together, the b's will cancel, and then you'll be able to have everything in terms of s, and you'll be able to solve that by using elimination. Okay, so that's how that would work, because I would have things written in terms of s, and life would be good. So let's move on to the next page, and we'll discuss more of these matters. Okay, so in this problem, I'm going to solve this by using substitution so that we can see what the result is, because we've talked about it, but you haven't really seen what it looks like yet. So since this is set up as a y equals equation, I'm going to use that expression for y, and I'm going to plug it in here. So to do that, I'm going to say 2 comes along for the ride, and then I'm going to write in 20,000 plus 1,500x. Okay, that's just substituting in for the y, minus 3,000x equals 50,000. Okay, so again, we're trying to figure out what is the x. So now I'm going to distribute carefully and rearrange my equation. So I get 40,000 plus 3,000x minus 3,000x equals 50,000. So what I'm seeing is that these are opposite signs. The 3,000s are opposite signs, so therefore I have eliminated my x's, not necessarily my goal, and I get this. So does that make any sense? So 40,000 cannot equal 50,000, so that's a not true statement. So I have an inconsistent solution, and what does that tell me? It tells me that my two lines are parallel. So if I had manipulated my second line to be a y equals, I would see that the slope, which is the coefficient to the x term, is the same in both, which would have tipped me off that I had a parallel aligned situation. Okay, let's go on to the next page. Okay, so just for an example, I'm going to solve this using elimination. So how would I set that up? So looking at those two equations, what I'm seeing is I like the way the first one's set up. So I'm going to leave it as 45x equals negative y plus 33. Now, for the next one, I'm going to move that to y. So I'm going to keep this as 90x equals minus 2y and then plus 66. Okay, so do you see that? So I have that going on. So now what should I do? What if I multiply both the top and the bottom by a just the top one by a negative 2. What will that do for me? So let's see. If I take this and I say negative 2 times that, what do I end up getting? And I'm going to put it down below here. I end up getting negative 90x equals negative 2 times a negative y gives me a 2y, and then I have negative 2 times 33 is a negative 66. All right, what's going on here? Okay, oh gosh, look what happens. This cancels. Ooh, that cancels. Ooh, that cancels. Okay, so what do I know? 0 equals 0. Is that a true statement? Yes, it is indeed a true statement. Okay, but it doesn't give me any additional information. So what is that telling me? That's telling me that one line is on top of the other line. And actually, I could see that if I manipulated my line so that they're both y equals, I will see they have the exact same slope. So this is a true statement, and it's a consistent statement, so I can say the solution is consistent, but dependent, because they're both the same line. So there's an infinite number of answers because these two lines intersect everywhere. So now you've seen what happens in that situation. So let's move on to the next page. Okay, one quick statement here. When you think about supply and demand curves, price is the y variable and quantity, or the x, is the x variable. And that is not really consistent with what we think about. This can be confusing since we usually think of quantity as a function of price, but this is just the way they write this. Okay, the reason why we have this in here is because they have a downward sloping demand curve and an upward sloping supply curve, and the equilibrium point is the solution of that system of equations. So that's the economic piece of a system of equations. Okay, so here we have some practice problems, and it says solve each system of equation using the method you think is most efficient. So let me tell you which method I think could be most efficient for some of these. So for example, A, since I see that I have different signs for negative 5x and positive 5x, I would add those together and use elimination to solve that system. For B, what I would do is I would multiply the top by 3 and the bottom by 2, and you would have then different signs on coefficients of 6, which would allow you to eliminate y, and I would solve that by elimination. C, looking at C, I see that I have t equals, so I would use substitution to solve for that. With D, since I have two z equals, I would just eliminate the z's, set those two equations equal to one another, and solve for my x, and then plug back in to get my z. Okay, so this is an algebraic operation for you. You want to go and practice this and make sure you're comfortable and that you are very careful with your algebra. When you plug your answers back into both equations, it should work both times. So that is a good practice for your algebra. So in this situation for problem number 4, they say determine the number of solutions without solving the system. Explain your reasoning. Okay, so how do you do that? How do you know you have the same exact equation? So you have the same exact equation when you write them in y equals format, and they are exactly the same. So that's a situation where you have an infinite number of solutions, and I believe that is going to happen in C, infinite number of solutions. So see if you can figure that out. Okay, when you have a situation where when you write them in terms of y equals, you have different slopes and different intercepts, you're going to have exactly one answer. That will happen when you have a situation like A, and I believe D does the same thing. Now, in situation like B, what happens is when you write them in terms of y equals, you find they have the exact same slope. When they have the exact same slope, the lines will be parallel and you will have 0 solutions. Okay, so just to recap, you should get one solution for A, one solution for B, or for D. And why is that? Because they have different slopes and different intercepts. Okay, for C, you should get an infinite number of solutions because they are the same line. And for B, you should get 0 solutions because when you write them in terms of y equals, you find they have the same slope, but different intercepts, and therefore you will not have a situation where the lines will ever cross. So see if you can write them in terms of y equals and draw the same conclusions that I just have. So in this section 3.3, it says reading between the lines, and this is the first time we're really talking about linear inequalities. So remember, if you have an equality, it looks like this. If you have an inequality, it could look like this, which is less than or equal to, could look like this, greater than or equal to, or it could be less than or greater than. These are termed strict inequalities because there's no equal sign. Okay, so let's look at the terminology for describing the shaded regions. So notice that in the first graph, graph A, the y values that are appropriate are everywhere less than or equal to y1. And that is why y1 has a dark line, because there is a partial inequality. Okay, so since it can equal the line y1, y1 is included in the answer. Okay, in graph B, look at the shaded area. And the shaded area represents where y is everywhere greater than y2. Why do I say greater here and not greater than or equal to? I say greater than because look at the dashed line. So the line y2 itself is not part of the solution. And the last case for graph C, you have what's called a compound inequality. Compound inequality means your y is kind of sandwiched in the middle, and then you have pieces on either side. So we're looking right now at the cross-hashed section. That's where we want to describe. So y, which is your answers, is less than or equal to y1. Notice the dark line. And simultaneously, y is greater than y2. Notice that you have a dashed line. Okay, so you want to read this section over carefully, make sure you understand what they're telling you, and be able to spot a compound inequality. Okay, also be familiar with the terminology of a boundary line. Okay, a boundary line can be included or not included. The boundary lines are basically the lines that you see in the solutions. If it's a dark line, it's a boundary line that is included. If it's a dotted line or a dashed line, it is a boundary line which is not included. Be able to tell the difference. Okay, I'd like you to read through this example 1, and I want you to understand, looking at this solution, I want you to recognize it as a compound inequality, and what we would say is that the desirable weight is less than or equal to the weight H and greater than or equal to the weight low. So basically the desired weight is in between the high weight and the low weight. It is not a strict inequality because you have a boundary line and a boundary line above and below that are both included in the solution, and therefore you have the equal sign. So it's a compound inequality, and it uses the boundary lines as part of the solution. Okay, this is an important little section called Manipulating Inequalities. And if you want to move your y around in your equation, or in your expression, I should say, so that you can read it and get more information, you want to follow some very special rules. They're enumerated here for you, but I'm going to switch things around over here, and I'll show you what I mean about working with these manipulations. Okay, the big takeaway that we're going to stress is that if you add or subtract, you are totally fine. But if you divide by a negative or multiply by a negative, it's going to flip this sign right here. So let's try to work with that. So I'm going to move my 2 to the right side. So I'm going to subtract 2 from both sides. That does not cause any problem. So I now have negative y is less than or equal to 7 minus 2, so that's going to be 5 plus x. Okay, so I do not need to know about negative y. I want to know about positive y. So I'm going to multiply both sides by negative 1. And the second I do that, it's going to change the sign on the negative y to a y. So that's great. That's what I want. But the piece that you need to really focus in on is the fact that when you multiply, the second you start doing that, you are going to flip that inequality. Okay, and you're going to end up getting, let me go back to my red, a negative 5 minus x. Okay, so that's the end result. And the big takeaway is that you have to flip the inequality. So let's do the next one. I believe the same thing is going to happen there. So I want to get my y on one side. So what I'm going to do is add 2 to both sides. So that means I have negative x plus 4 plus 2 is greater than y. So what can I do at this point? Well, I want to not read it like that. I want y to be the leading one. So let's combine like terms first off, and that gives me negative x plus 6 is greater than y. Okay, well, how is y related? So in this situation, I'm not multiplying by anything, but I'm going to read it backwards. So start reading from y. So y is, reading from left to right, less than negative x plus 6. So that is another reason for flipping it. When you want to read about your y, you're going to need to flip it. Okay, and there's one more we're going to do on the next page. Now, I thought I had a picture of that last problem, but I did not. I'm just going to write it here for us. And looking at this, I'm going to add x to both sides. I end up with negative y is less than, if I add an x, I have 3x plus 17. But remember what I said before, I don't care about negative y, I want to know about y. So this time, think about dividing by negative 1. Divide by negative 1. Whenever you multiply or divide by a negative, you're going to flip that inequality. So that's going to be y is greater than negative 3x minus 17. Okay, so be very cognizant of when you flip the inequality. It's not when you add or subtract, it's when you multiply or divide by a negative. That's going to flip your inequality sign. Okay, this example is worth reading through and the solution as well, because it introduces an economic situation once again. So you have cost versus revenue, and the break-even point is where cost and revenue are equal, and that's right here. So what we have is a system of equations, and you're looking for the point where your x equals y, and in this situation your x is your tons of fertilizer and your y is your cost. So at the break-even point, you have the right amount of fertilizer and you are having the right prices. So read through this example, make sure it makes sense to you, and make sure that you understand the break-even point for economics is where costs exactly equal your revenue. That's where you're neither losing money nor making money, you are breaking even. Okay, here's a page of nice practice problems to do. I see that I have a break-even situation going on here. I have inequalities here that I can look at graphically. They want me to solve these graphically, so I'm going to need to graph them. Now, a point about graphing. It's an inequality, so it says, for example, for A, y is greater than or equal to 2x minus 1. And then what you're going to do is you're going to say, I'm going to graph it just like y equals 2x minus 1. And then I'm going to say to myself, okay, I'm going to plug in a 0, 0. and see if that is a good solution. So for example, let me just do this here so you can see my decision criteria. Because it says greater than or equal to, I can have a solid line. So -1 is here, and let's just say that my slope, it goes up by 2, so it's somewhat like this, okay? So the point 0, 0 is not in my equation, not on the line. Hopefully we agree with that point. Okay, so there's the point 0, 0, kind of an orange. Let me make that a darker color. Okay, so I'm making it kind of purple. Okay, there's my point 0, 0 right here at the origin. So what I say to myself, how do I know which way to shade this? I know that the line is part of my solution, but then do I shade up or I shade down? So the purple point is the point 0, 0. So plugging in 0 both places, I get 0 is greater than or equal to -1. And is that true that 0 is greater than or equal to -1? Well, clearly it's greater than -1. So therefore you're going to shade to the truth. So shade to include that point. Okay, that's how I decide which way to shade. Pick a critical point that's not on your line. Check that solution out. If the solution is a true statement, then shade to include that point. If the solution is not a true statement, then shade away from that point. Okay, and you'll always have the correct solution if you do that. Okay, so let's go on to the next page. Okay, this last page I thought was very interesting because they're giving us 3 equations and 3 variables. And they walk you through this very nicely. So I will say that you should definitely follow this. Follow it exactly to the T. And when you do that, you should be getting the following answers. Your x should equal 3, your y should equal 5, and your z should equal 10. See if you can follow these steps as they are laid out and get those same answers. And when I see you again, we can go over any of this material because I'm going to have a problem set that's due as well. So make sure that you come with good questions and we'll answer everything, and we'll be all set for this section of Chapter 3.